The Young's modulus of steel, 200 gigapascals. And of this aluminum, it is 70 gigapascals. They both have that same diameter of 12 millimeters. The length of the steel piece, I'll start with steel, is 3 meters. And the aluminum piece is 2 meters. And under this loading, we're asked to find two things. We want to know how far was B displaced and how far was A displaced. I'm going to call that big delta B and big delta A. So usually for my notation, I use capital delta to designate for a system how far it moves relative to a stationary point, and the lowercase delta will refer to the deformation in a section. We need free body diagrams. Again, we need a free body diagram for each section normally, but basically anytime we're changing the material, the cross-sectional area, or the internal load, we have to make a cut through that piece and represent it in our free body diagram. In this case, if we look from C to B, it's a constant material, it's a constant internal load, there's no applied loads between C and B, and it's a constant cross-sectional area. So I can make one cut through CB that's going to reflect everything between C and B. I don't need to make an infinite number of cuts here because every free body diagram will look exactly the same. So I'll begin with picture number 1, a cut through CB. I have the option, just like I did before, if I make an internal cut here, I can take everything to the left or everything to the right. In this case, there's a wall here. I don't care what's happening at the wall, so I can make a cut through here and take everything that's happening to the right of that cut and use that as my free body diagram. Now this is a statically determinate problem. I can, if I wanted to, if they asked me, I could find the reactions at the wall at C. In this case, I don't need to, so it's going to be easier to just draw this picture. But we'll see in the next example, we can't avoid it. If I take everything to the right, I can see both of those applied loads. And where I made that cut, I'm only worried about I'll call this piece steel, I guess. Steel is AB, yeah. The free body diagrams don't care about material or those type of things. It just cares about forces and moments. That's my complete free body diagram for my cut through the steel piece. Then I need another picture for when I cut through the aluminum piece. Between A and B, there's a constant cross-section, a constant material, and between A and B, I don't have any point loads being applied. So those three things are constant, so I can make one cut through AB that reflects the entire section from A to B. Again, I can take everything to the left of a cut or to the right of the cut. I'll take everything to the right of the cut. As a note, and we'll see this, if I say had a point load in the middle of CB that I was applying to the left or to the right, I would need a third free body diagram because I would need one cutting to the left of where that point load was, another one to the right of that point load, and then another one through here. Also, if I didn't have a point load here, if the 6 kilonewtons were not here, I would still need to cut through AB and through CB because even though the internal loads would be the same and the cross-sectional areas are the same, the material changes. So I still need to cut through each section there. From the free body diagram, now we can go to the equation step. From the recipe before, we start with the equilibrium equations using our free body diagrams. From the first free body diagram, if I sum forces in the x direction, I'm still in static equilibrium. I'll have negative P steel minus 6 plus 18. And free body diagram 2, I'll have negative P aluminum plus 18 kilonewtons. So while I'm here, I'll solve for these values since I can. The internal load in the steel is 12 kilonewtons, or 12,000 newtons. And in the aluminum, 18,000 newtons. And these are both tensile. Because it's statically determinate, we can find those as numbers right now. When it's statically indeterminate, like we'll see next, we might just have to hold on to these equations. But if we solve as we go, it makes it a little bit easier. If this were at 211, we would be done. We found equilibrium equations, huzzah. But now we have to keep going because there's 4 substeps now in our equations. Equilibrium, we have as many equilibrium equations as we have free body diagrams, and we're done. We're out of equations to use. However, what we're asked to find is how far does the point B travel? How far does point A travel? So we need more equations to find what is unknown. This is the compatibility equation step. This is where we're going to look at how do the deformations of the sections relate to the deformations of the system. In this case, if we're interested in big delta B, using our sectional deformations, how can we find how far point B travels? Equal to the deformation of the steel, I'll call it, or BC, whichever you call it is fine. Like since the steel is all under one section, that's easy to just call it steel. But like if I have point load, I might have one piece of steel and another piece of steel. Then you're probably going to what I call it like AD and then DB or something like that. So right, it travels as far as the steel deforms. We're always operating on the assumption, because we're assuming tension is positive, that a positive deformation is an elongation, a negative deformation is a contraction. And if we're interested in how far point A travels, how can we compute that?
Even that deformation of the two.
Right, so however much the steel expands or contracts, plus how much the aluminum expands or contracts, that'll be delta steel plus delta aluminum. Right, so the sum total of their deformations, and some pieces could be shrinking, some pieces could be growing. They don't all have to be going the same way. So if these both expand, we add them together, then point A, the sum total of that expansion of each piece. For each section, we now want to compute how much does that section elongate. This is where we relate the deformations to the internal loads. We have 2 sections. One of them is, we can compute the deformation of the steel. In this step, if we had a thermal factor here, if the temperature were being raised or lowered, we would include it here. But otherwise, we only have to include the mechanical deformation, which will be the PL over EA. But we want to keep in mind that we're evaluating it only for this section. So we have to use that section's Young's modulus, that section's cross-sectional area, that section's internal load, and that section's length in this calculation here. So for this, we want to use P sub steel, which we actually found as a number. It was 12,000 newtons. The length of the steel is 3 meters. Young's modulus of the steel was given to us, 200 gigapascals. And the cross-sectional area of the steel we can compute because we know its diameter. And it's round, so it would be pi over 4 times 12 times 10 to the negative third squared. It's for reasons like this that I suggest always use base units to have less confusion here, because this would be kilonewton. If I did not use base units, it would be kilonewtons over gigapascals times millimeters squared. So it would be a milli squared times a giga, and then a kilo over that. I think it's going to be much easier to go with base units here, and it avoids all that confusion of remembering all the prefixes that you were using. Everything here is in, so newtons, pascals, meters squared. Makes your life a lot easier. In this step number 5, these are all numbers at this point, so we can find the deformation of the steel. That is going to be 1.59 millimeters. Then we want to relate the deformation of the aluminum to its internal loads. So it's the same equation, but now we have to use the aluminum sections P, L, E, and A. We already determined that its internal load was 18,000 newtons. It has a length of 2 meters. Its Young's modulus is only 70 gigapascals. And it has the same cross-sectional area that the steel did. For the aluminum piece, it's going to elongate. These are both positive. I will include that so we remember. Positive 4.55 millimeters. Now we can go back to equation 3. We know delta B is just delta steel. That's also 1.59 millimeters. And that's going to be in the picture. It will travel to the right. Now we add them for the total travel of point A. We add delta steel plus delta aluminum is 6.1 millimeters. And that will also be to the right. For these, we do want to interpret which direction are they traveling. Since they're both expanding, then point A is being pushed to the right or expanded to the right.